By the way, for those of you who think I'm going very fast in this, I gave another summer school at the beginning of this summer, which was a week long. Everything we've done up to this point was my first day. So this is distinctly the slow version. So what we're going to talk about today is we're going to get into notions of rigidity and almost rigidity. Primarily, we'll focus on rigidity today. So, I mean, for really all nonlinear PDEs, I mean, not just the Ricci equation, your first step in trying to prove structure theorems and eventually regularity theorems, I mean, good ones that kind of go beyond generic statements, is to find situations where if you're handed a solution and you're told the solution has some other property, then this is very hard to happen. It forces some sort of very rigid situation to occur. And it sounds like that may not actually be very useful for a generic solution, but in practice, perfect, thank you. But in practice, what happens is that you're able to sort of take one solution and produce from it other solutions that always do have these rigid properties. For instance, in our context, how would you do this? Maybe you have an Einstein manifold, and you start looking at tangent cones. So the point is you've gone from one Einstein manifold to other Einstein, or limits of Einstein manifolds maybe, or limits of spaces with lower Ricci curvature, to other spaces which are limits of spaces with lower Ricci curvature. But somehow they're going to be more rigid than your original space was. So you're going to be able to prove something more about them and then use the fact that these things exist at every point to sort of say something about your original space. So you really want to say something about spaces with solutions that are not just arbitrary but have more structure. There's two types of rigidity that we'll really focus on today. One's the splitting theorem, and the other is volume rigidity. We'll start with the splitting theorem because I think historically it's sort of really the first in this context that appeared. The splitting theorem really sort of arose first, well actually it arose first in the two-dimensional case, but then more generically it arose for spaces with non-negative sectional curvature first. This was done by Toponogoff. And then Cheeger and Gromall came around and realized that this was a statement that really held for non-negative Ricci curvature, although their proof is really quite distinct. So let's just start with the statement, and then we'll kind of bust our way through understanding it. The theorem. This is the splitting theorem. Cheeger and Gromall. So it says, let's take some Riemannian manifold, complete as always, with non-negative Ricci curvature. Now, our big assumption here is this. We're going to let gamma, so from minus infinity to infinity to m. So this is some curve in m, but it's a line. I.e., what this means is that the distance between gamma of s and gamma of t is equal to s minus t for every s and t. So what that's saying is that this is a geodesic, which is minimizing and infinitely long in both directions. And then, in fact, the conclusion is that M is isometric to R cross N, where N also has non-negative Ricci curvature. So in other words, if you have a complete space with a line, an infinitely long geodesic in both directions, then this can only happen if you actually split off an R factor. And our line in this case, I mean, you can identify, right? I mean, well, what's the natural line here? The natural line here would be something just something that fixes this point and then runs along this guy. So in these coordinates, gamma of t will actually just be Tn. Some n. So this line has to come from like a global R factor. Okay. So let's sort of punch our way toward proving this. So how might we actually go about proving this? So first, let me start with sort of an overview of what it is that we want to actually construct here. So what we want to construct here in the end, then this is going to be sort of a statement that actually doesn't itself depend on the non-negative Ricci. So what we want is a function f, some nice smooth function f, from M to R, with f, well, not being identically a constant, but the Hessian of f, the second derivative of f, is identically 0. Obviously, say if we're on Euclidean space, I mean that this is what a linear function is, right? I mean, it's a function whose Hessian vanishes. But the basic claim here, and I'll sort of tell you what the main points of this claim are, but since this has nothing to do with Ricci curvature, we won't prove this carefully. However, I'll give you the main points, and the points are absolutely provable if you're sort of given to them one by one as sort of homework assignments. They follow from the condition pretty easily once you're sort of told the right order. So the claim is that for any complete M, if such an f exists, then M is isometric to R cross N. With, I mean, under the correct coordinate charts here, f of t n is just equal to some constant a times t. So, I mean, n here can be identified, the point is, with the level set of f. So what we're saying is that if you have any nice, smooth, complete manifold, and there's a function on it whose Hessian vanishes, then you actually have to split an R factor, and this is an honest-to-goodness linear function on that R factor. That's what's being said. It actually only sees that R factor as a function, and it is an honest linear function there. So it's a very rigid thing. It's very tough to happen. I mean, I'm not going to say proof. I'll just sort of say main points of proof. Of the claim. So how do you do this? So the point is that already you've sort of seen what you want to identify. Just from the statement, you've kind of seen how you want to identify this n factor, at least. You want to identify this with the level set of your function. So how would you identify the rest of M as actually somehow being foliated by such a level set? Well, there's a natural thing to do. So that is, you let phi t from M to M be the diffeomorphism of M, be the gradient flow of f. Right, so what this means, right, is that as a function, ddt of phi t of x is, say, minus the gradient of f evaluated at phi t of x. Right? For any nice smooth vector field, namely the gradient of f, such a flow exists, and it gives rise to a diffeomorphism of your manifold. So we're just going to consider this guy. And now the main things you want to show here are the following. So first thing you want to show, well, under the assumption that the Hessian vanishes, the gradient of f is identically equal to some constant. So it doesn't depend on what point you're staring at in the manifold. And this constant, by the way, being non-zero by our assumption that the function itself is not a constant. This is a nice little computation. I mean, it's simple enough. It follows from the Hessian right away. It's worth doing. What does that tell you automatically? Knowing, I mean, what happens if you have well, I mean, so what happens actually if you have now a gradient flow of f like this, where the gradient is a constant? Then in fact, you can prove that this gradient flow, phi sub t, maps level sets to level sets as a diffeomorphism already. So in fact, just this statement here tells you that M splits topologically as a product, R cross N. You can get that just from this, the topological splitting. To get the geometric splitting, you want two more properties to show. Namely, you want to show that the phi sub t is an isometry for every t. Note, what do you need to do that? You need to know that this is a killing vector field. Right? That means that the Lie derivative of the metric with respect to it is supposed to be 0. And what is the Lie derivative of the metric with respect to this? If you do your computation, it's just the Hessian. Right? So I mean, that's the hint of how that comes out. Good computation to do, though. In general, for a vector field, it's supposed to be the symmetric part of the gradient, right? But the symmetric part of the gradient of something is just the Hessian of that thing. And the final necessary ingredient, so even these two are not quite enough to get a splitting. But the final point here is that if you look at the curves, let's not call them gamma, let's call them sigma t, which for some point x, I just want to look at, so I fix x, and then I look at the curve generated by sigma t. So it's just some curve here. And these are all geodesics. Okay. And basically, this gives you topological splitting, and these two will give you isometric splitting. This is rough because I don't want to spend too much time on it, but these are the main things. Okay, but the point is that regardless, our main goal is to build such a function now. So what we need to do is under this context here, where we have a space with non-negative Ricci curvature and a line, we have to see that there exists some function on it whose Hessian vanishes, but which isn't a constant. So how do we do this? So and the key tool here, which is a really nice one, by the way, is called a Boozman function. So let me first describe to you not just maybe one function, but let me give you a whole bunch of functions, and we'll use this to eventually build a function. Let's draw a nice little. So we're inside our space with non-negative Ricci curvature, where we have our line gamma here that's supposed to go back and forth forever. Let's pick our center point P, which is maybe gamma of 0. Just define it by definition. And let's consider the following function. So for some other t fixed, let's let bt sub p, I'll call it, of x be equal to just the distance from x to gamma of t minus the distance from p to gamma of t. So pictorially, here's gamma of t, here's our point x. We're looking at this distance and then subtracting off this distance here from it. And we're doing this for any given t. So for every t fixed, this gives us a nice function on our manifold. So before I try to give you an intuition for what this function is supposed to mean, let's write down just 3 really basic properties of this function. So the first is that, well, maybe I'll turn it into 2 properties. Its value at p is 0, right? So we've normalized so that all these functions, no matter what t is, the value at this point here is always 0. I mean, that's the normalization here. That's all we're doing. Right? It's like this is a distance function. Like we want to work with distance functions, but we don't want them blowing up. So we subtract off the distance from these 2 points, so its value here becomes 0. That's all. So it's a normalized distance function. The fact that it differs from a distance function by a constant also tells us that the gradient of BTP is identically 1 at every point. So it's a Lipschitz function, right? It differs from a distance by a constant, and so its gradient is 1. That's our first property. In particular, it's bounded on compact subsets independent of T, right? Second property, which is relatively interesting, is that if S is less than T, so now I want to compare two of these guys. So if S is less than T, then what can we say about the difference? Then BT sub P of X minus BS sub P of X. Well, this is equal to what? This is equal to, let's just plug in the definition. This is the distance from X to gamma of T. Minus the distance from P to gamma of T, minus the distance from X to gamma of S, minus the distance from P to gamma of S. Plus, thank you. So if this is gamma of S, then what we're saying is we kind of have this set up here where we're looking at this distance minus this distance minus this distance plus this distance. So what is this distance minus this distance? So that is this guy minus this guy. Well, I mean, this is a geodesic. So the distance from I mean, this is not complicated. The distance from gamma of T to P is just T. The distance from gamma of S to P is just S, right? I mean, I could have just written T here instead, right? I chose to write it this way so that we could see it in terms of distance functions and normalizations. But this is just T and S, which is to say we can rewrite this as being, so this is S minus T, or minus the distance from gamma of S to gamma of T. This is the more convenient way of writing it. This here is just the distance from X to gamma of T. And this thing here is just minus the distance from X to gamma of S. So what? So what we have written here is that we have the distance from here to here minus the distance from here to here minus the distance from here to here. Well, this is the triangle inequality, right? I mean, the one thing we know about distance functions is that this guy here is less than or equal to this plus this. So that is to say that this guy here is less than or equal to 0. So if we skip all of that, we have this is less than or equal to 0. Now, all computations aside, all we're saying is that as T increases, this family of functions is behaving in a monotone way. Right? Well, we're saying that the functions are decreasing as T increases. Right? And our third property is that if we look at the Laplacian of the distance function, again, I mean this as a measure, if you want, or as a distribution, then we've already, I mean, these two have nothing to do with Ricci curvature, right? Ricci curvature has not entered yet in all of our computations. This is where Ricci curvature enters. This distance function here is actually less than or equal to n minus 1 over, well, it's just the distance function from X to gamma of T. which if we want, we can rewrite as being, well, no, let's not do that. Let's keep it that way. So what's the key point about this guy here? If we fix x, then as t gets big, this is going to 0, right? That this distance here is going out to infinity, so that it's looking more and more like a superharmonic function as t goes to infinity. Okay. These are the three basic properties, and so what? I mean, what do we do with all these things? The main point is this. We don't want these functions. What we want instead is we're going to define b plus and minus. Yeah, let's just do plus first. Of x. Let's define a single function as being the limit as t goes to infinity of bt sub p of x. So let's first see this is a reasonable definition, and then let's just see what it is, at least in a simple example, so we can suddenly have some intuition for what the heck is going on here. So this exists why? Well, these things are uniformly bounded on compact subsets by 1. At the same time, as t increases, they're monotone. So for x fixed, this is a monotone decreasing sequence, which is bounded below. It converges. Right? So when I say limit, I mean there's no subsequence, there's no nothing going on. It converges. Right? So this is a completely reasonable sort of definition in the first place. More interesting now, let's just ask, well, what is this in a simple situation? So what if we're on Rn? So what's a reasonable line on Rn? I mean, a line in Rn is just an axis, right? I mean, it's an infinitely long geodesic. It's an infinitely long line. It's an axis. So for instance, gamma of t, and this is an example here, could be just t0, 0. So we look at the straight line out. Here's our origin, which is our p gamma of 0, and our line goes out. If we fix some point x, then what happens as we take points out here and we look at this distance minus this distance? Well, as these lines keep getting further and further out, this line gets more and more horizontal, right? So that this distance going out minus this distance going in, well, it's converging to just, I mean, the difference here is just that length there as you go out, which is simply to say that b plus of x is simply equal to, well, I guess since it's this minus this, it's minus x1, the first coordinate. So it's a coordinate function. So what we've done is we've built a geometric way of constructing a coordinate function on the manifold, which, by the way, if you think of this another way, is a line. It's Hessian vanishes, right? So, I mean, in some sense, if the theorem were true, the splitting theorem were true, right, then somehow this process here would have to give us a coordinate function. It would have to give us the projection. So even if we don't know if it's true at the moment, somehow it has to come from this function, right? So we have this geometric way of building it. So now our hope is to actually see it does come from this function. And by the way, it'll be technically useful to actually consider not just b plus, but b plus or b minus by taking the limit to either go to plus infinity or minus infinity. So b minus here would have been, so it's either minus plus the coordinate function here. So these two things only differ by a sign on Rn. Right now they could be, I mean, an arbitrary manifold, they could be completely different functions. But on the Rn, they just differ by a sign. They're plus or minus the coordinate function. Okay. So our goal then is simply to see that b plus and minus will define a coordinate function on our space. So how do we do this? So let's just start with some properties of b plus and minus. So let's start with two easy properties. So first off, well, I mean, it's a pointwise limit of a sequence of functions whose Lipschitz norm is exactly 1, at the very least bounded above by 1, right? So that means that we certainly know this. Sequence of functions with a Lipschitz bound converge to a Lipschitz function with the same bound. Well, we're going to see exactly 1 in a few minutes, but I'm just saying a priori with no work, we know it's at least bounded by 1, just because it's a sequence of Lipschitz functions with some bound converging. And the second point we know about these things is that the Laplacians at b plus and minus, well, for the x is fixed there, so on any x, so for all compact support, we see it's going to 0, and we have that it's actually less than or equal to 0 then. And again, this is from just limiting out some distributions. So I think what I'll do here is I'm going to write down two technical claims. And before we prove the technical claims, let's just see why, once we have the technical claims, we can prove the theorem to give some motivation for doing all this technical work. And then we'll come back and we'll prove the claims. So these are two things that we would kind of expect to be true, like based on, say, our example on Rn. Okay, so the first thing is that the gradient of b plus minus at any point is exactly 1. So this is our first claim. So if this is supposed to be something whose Hessian vanishes, then certainly we would expect this to be true. Claim 2. And now the motivation for this claim should come from the example, and that's that b plus of x plus b minus of x is identically equal to 0. So right, a priori, these were just random functions, two different functions. But in our context here, we're going to see that they're minus each other, just like they are in Rn. Just like they should be if they're coming from an R factor. Okay. So let's prove the splitting theorem based on these claims. So what does 2 really give us now? So just to be explicit about it, let's let f be b plus of x. So the point is that this is supposed to be our function from the beginning, whose Hessian is vanishing, and the gradient is a constant. Certainly the gradient of this thing, well, the gradient of this thing is a constant comes from part 1. That's fine. But we need to see if the Hessian vanishes, and this still takes a little work. The most interesting thing here is the following. So we know the Laplacian of f. Well, we already know it's less than or equal to 0. But now, since we know that f plus b minus is 0, or b plus b minus is 0, this is also precisely equal to minus the Laplacian of b minus of p. But the Laplacian of b minus of p was less than or equal to 0, which means minus it is bigger than or equal to 0. So we at least get that f is harmonic. Now, certainly if we're expecting the Hessian of f to vanish, the Laplacian of f vanishing is a requirement for this, right? but we want to see that this is actually sufficient. Why? Well, how do we get from the trace of f vanishing to the whole Hessian of f vanishing? And the key point here is that you've got to combine with claim 1 again. How can you have a harmonic function with constant gradient is the question. So to do this, what you should do is use the Buchner formula that we've been using over and over again. So we have the Laplacian of the gradient of f squared. So this is a harmonic function, so that means it's precisely equal to 2 times the Hessian of f squared plus 2 times the Ricci of gradient of f, gradient of f. But on the one hand, well, I mean, we have non-negative Ricci, so we can drop this term. But on the other hand, this is 1. We're taking the Laplacian of a constant, so this is just 0. So we have the Hessian of f squared is less than or equal to 0. Well, I mean, it means the Hessian of f is 0. So we have a function with constant gradient and vanishing Hessian. Well, we don't have to assume the constant gradient. You actually get that from the vanishing Hessian once you have that point, but non-zero gradient, I guess, is the real point. And vanishing Hessian, and the point was that this function defines a splitting function on our manifold. So we're done. So once we know claims 1 and claims 2, we know that, well, either b plus or b minus for that matter, are functions with vanishing Hessian. They're harmonic functions with vanishing Hessian. They're smooth. Right, so I mean, this is regularity theory, so we certainly won't go into this, but just to mention it. I mean, if you have a priori f wasn't a smooth function, right? It was a Lipschitz function. But if you have something whose Laplacian vanishes in a distributional sense, right, then it is actually a smooth function. This is regularity theory. Okay, so we have to prove claim 1 and prove claim 2. Claim 1 is not so bad. Claim 1 is actually very generic. It doesn't really depend on much. Claim 1 is really something that would hold for really any Boozman function without the non-negative Ricci. I mean, this is not so important for claim 1. My chalk. So, well, we have a nice picture there, but I'm going to have to redraw it anyway, I guess. So how do we see that this, I mean, this is a Lipschitz function, right? So how do you see something like this for a Lipschitz function? We're not going to actually take a derivative, right? I mean, it's a Lipschitz function. You don't take derivatives. So what you do is you need to find, I mean, we fix x, and you need to define xs such that the distance from x to xs is equal to s, and such that the Boozman, I mean, just do it for p plus. I mean, it's exactly the same with the two. And b plus of x, and I'm going to drop the sub p just because I'm tired of writing sub p, minus b plus of xs is equal to s. So if you could find such a family xs that satisfies these two things, you're definitely done. Right? I mean, certainly that means that the Lipschitz norm is exactly 1. Right? I mean, that's the definition of what this thing is. So you divide by the distance, which is s, and you have 1 for all these things. It's not just converging to 1, it is 1 for every s. And pictorially, this is actually quite simple. So let's do this for bt of x is the point, and then we'll just limit out these points. So if here's our p, as usual, here's our x, here's our gamma of t, then what do? Take x and look at the geodesic, call it sigma, whatever, from x to gamma of t, and move a distance s along it. Well, I mean, if we want, we can shove a t here to signify this is supposed to be to gamma of t, and just call this point xts. And by definition of what this thing is, right, it's the distance function from here to here minus the distance from here to here. So if we look at this guy and this guy, and we look at the difference between the b sub t of x and b sub t of xs, I mean, it's just this distance here. It's the only thing that survives and didn't get canceled out. So it's exactly s. And of course, the distance between x and xst is precisely equal to s. By construction. I mean, we just move distance s along a minimizing geodesic. So the point is now, as you just play the same game, as t goes to infinity, what happens? I mean, you just get your points, and eventually your rays converge out to something, and we let these xts's converge to something. Here's our xs, which is the limit of xts. And everything going on here is pointwise convergence, which means this converges pointwise, these converge pointwise, everything is fine. So they converge and give us something for which B plus actually satisfies these conditions. Sorry, I think the picture is getting a little busy. That's it. And that's where gradient 1 comes from. So the point is that for every point, we know there's a direction we can move to make it go in unit speed, to increase in units, namely like the direction of this sort of corresponding ray here, right? We move in that direction, and it's increasing at rate 1. That's what Lipschitz 1 is. And proof of claim 2. Now this one's much more interesting. I should point out when this was first done in the original papers, I mean, the understanding of this distributional Laplacian of the distance function was not really done. That it had this upper bound on the Laplacian in a distributional sense was not really known, nor in a barrier sense or whatever sense you mean. So that somehow, I mean, it's kind of obviously implicit in their proof that they're kind of doing this, but this was not quite how they thought when they were doing this. I mean, implicitly, this is what they were doing, but they had to work a little harder. Okay, so how do we see that b plus b minus is 0? So first, call this A. We have that b plus of x plus b minus of x. And so it's bigger than or equal to 0 everywhere. So as usual from pointwise convergence, it's enough to do the following. Let's show that bt of x plus b minus t of x is bigger than or equal to 0 for every x and t. Then by limiting t to infinity, we just get these statements here. This statement here really uses it. This is a line, by the way. So here's our gamma of 0. Here's our point x. Our picture is that here's gamma of t. And here's our gamma of minus t. So let's just compute this thing out and see what we get. Up until now, I have not used that it's a minimizing line. That's right. That this is the one and only place where it's used as a line. And the Ricci curvature, just for those of you really paying attention, is used in 2 places. All right, the Bachner formula was one place, and the upper bound of the Laplacian was the other. Yeah. Property this? Yep. Yeah, so this here was less than or equal to m minus 1 over the distance from, Why can you limit this out? Okay, I mean, this is a distributional argument. I'll be a little rough, but it's actually not hard. So imagine, so this is in a distributional sense, right? So pick some smooth function phi with compact support. So what do you really, I mean, what is this statement? It's the statement that the integral of the Laplacian of phi times bt is less than or equal to the integral of phi times n minus 1 over our distance function, right? From x to gamma of t. Phi here has compact support, right? So what we want to do is do this computation when t goes to infinity, right? This is some smooth function with compact support. This is a Lipschitz function. This converges as t goes to infinity to the actual value of the Laplacian of that. So as t goes to infinity, this to the t actually converges this to infinity. Make sense? Here. I mean, instead of erasing it, it would have been better to actually write an extra line, but I had to erase claim 2, but oh well, I've got claim 2 written over there anyway. It converges pointwise to it. I mean, it's a Lipschitz function. It's actually pretty nice. So I'm saying that this actually, for each phi fixed, it actually converges to this integral. Because this is just some smooth thing with compact support, and there's pointwise convergence going on here. Right? And this guy here, well, pointwise convergence to 0. Right? That's it. Which is, what's that? Sure. Okay, for this to be non-negative, it's got to be, sure. I mean, non-negative means that if this is non-negative, then that this will actually be less than or equal to 0, right? That's right. So it'll be not converging to 0, I'm sorry. It'll be going to an upper bound of 0 if phi is non-negative and smooth. Yep. Wait, where were we? Okay. So we're trying to prove claim 2. We're trying to show that this plus this is 0. Okay. It's enough to show that bt plus b minus t is 0. So the first thing we're going to do is show that bt plus b minus, b plus b minus is bigger than or equal to 0 is the first thing we want to show. And that's enough to show that bt plus b minus t is bigger than or equal to 0. Pointwise convergence, right, just means that we always get to work with the t's. So that is, it's the distance from here to here minus the distance from here to here plus the distance from here to here minus the distance from here to here. We want to see this is non-negative. Why is this true? In fact, this is just the triangle inequality and the fact that this thing is a line. So the point is the distance from here to here plus the distance from here to here, because it's a line, is precisely equal to the distance from gamma of minus t to gamma of t. So what do we have? We have the distance, this distance plus this distance minus this distance. I mean, this is the triangle inequality. This is always bigger than or equal to 0 for 3 points, right? We've got 3 points, and we're looking at the differences of the distances. So this is not negative. So when we take a limit, we get that b plus b minus is less than or equal to 0. So now we've used line to prove claim 2. We have not used the Ricci curvature condition yet to prove claim 2, and the Ricci curvature condition is important. So we can't take an arbitrary complete thing with a line and expect that b plus b minus is 0. This is not reasonable. So how do we pull Ricci curvature into this? So this is really a nice argument. So let's mention one more point, and that's that b plus, if we're on the geodesic, then b plus b minus of gamma of t is identically equal to 0. So that is, if we take our two Boozman functions, the sum, and we restrict them to the line, then we have actually 0 on this. And why is that true? It's the same argument, but now you have equality, right? Because x is replaced by gamma. Let's call this s, so there's no confusion. So replace x by gamma of s here, and you have actual equality, right? It's the same argument. But what's a and b mean? It implies that we have a function, b plus plus b minus, which is bigger than or equal to 0. It attains a minimum on the geodesic. And we have one more thing. Each of these things are superharmonic, so the sum is superharmonic. What should be screaming at you at this point is strong maximum principle. What does the strong maximum principle say? It says if you have a superharmonic function, if it attains an actual minimum at some point, then it has to be a constant. Well, it's non-negative. Since it's 0 here, it's actually attaining a minimum at some point. So that means that b plus plus b minus has to be a constant. Well, since that constant's actually got to be 0, at least along the line, it's got to be 0 everywhere. Okay. So that's it. Now we've proved claim 1 and claim 2. So now the point is we do what we did a few lines back. We define f to be this. That means that f is harmonic, and it's harmonic with constant gradient. And you show this to Hessian as vanishes, and we're done. Still true. Still true. The easiest way to see this, by the way, as I say on Rn for fun's sake, is to take something who solves this in a distributional sense, say flow it by the heat flow to smooth it out. So don't just smooth it out arbitrarily, but by the heat flow. It'll actually preserve this condition, but give you a smooth function. Right, so now you can actually just use the smooth function version and apply it for the. That is in general how you prove things for distributions. Smooth them by heat flows, it preserves Laplacian everything, right? And then you can just do stuff for smooth functions and limit back. Okay, great. Well, let's move on. So that's the splitting theorem. Let's at least state one more rigidity theorem. I mean, actually, you know what? Instead of that, let's discuss a minute the who cares factor of this. So how are you going to use this? And I should be very clear that what I'm describing to you is morally correct, but there's a 40-year gap between this theorem and actually using it this way. It's very hard to use it this way. What you have to do is replace this with what you call the almost splitting theorem, because essentially you're going to want the splitting theorem to hold not just for smooth manifolds with non-negative Ricci curvature, but you need it to hold for limit spaces of smooth manifolds with non-negative Ricci curvature, and proving that's a very tricky business. It took a long, long time to prove that. I mean, you basically had to prove an effective version of it on smooth spaces that you could limit out. But I mean, well, we'll get to this next week, but it takes more. But nonetheless, let's just pretend that this splitting theorem holds on limit spaces, right? So let's study some sequence of spaces like yesterday. Okay, they can have points. I don't really care. The Ricci curvature is uniformly bounded from below by something, unless them converge to some space. Roughly, how do we get a structure theory out of the splitting theorem? How do we say something about the structure of this space just knowing this? So let's pretend that the splitting theorem held on X2. It does, by the way. It's going to take more to prove it. But let's pretend that for the moment. So how could you get something out of this? Well, so let gamma be any geodesic on X. So X has lots of minimizing geodesics in it. Just pick your favorite. And look at some interior points. Then let's look at any tangent cone at this point. Then what can we say about this? Well, so remember, I mean, this limit exists. I mean, this Gromov-Hausdorff is a reasonable thing to look at by our compactness theorem yesterday. Tangent cones always exist at every point, so this is not an unreasonable thing to look at, right? Because they're also they're also sequence of spaces with lower Ricci curvature bound is the point. So the same compactness theorem from yesterday applies to say that for any sequence of dilations, a subsequence will actually converge. So we've got tons of tangent cones at every point. But now, this space here is a limit of spaces, which maybe they don't have non-negative Ricci, but remember, we're blowing up X to get to this thing. So when we go blowing up these guys to converge out to this guy, the Ricci curvature is going to 0. So you can view this as being a space with non-negative Ricci curvature. So it's a space with non-negative Ricci curvature. We'll just say it does. And this geodesic, right, is an interior point of a geodesic. But when we look at this point, right, I mean, this is some finite geodesic maybe, but we're in the interior, and we start blowing it up, what happens? This geodesic gets bigger and bigger and bigger. So that in the limit, there's an actual line on this, just by being on the interior of a geodesic. So every single tangent cone here, this thing actually has to look like R cross something else. So automatically, whenever we start on the interior of a geodesic, we actually have that every tangent cone splits an R factor. But now it's actually not so bad to prove that, I mean, so how many points lie on the interior of a geodesic? Well, almost every point does. Not literally every point, but away from a set of measure 0, every point lies on the interior of a geodesic. So every point splits at least one R factor when you blow up. But now what do? Basically, roughly, you iterate this process. I mean, you kind of view this also as being a space with non-negative Ricci curvature. There's got to be a geodesic in there. You find the interior of one of those points, and you blow up there, and now you split 2 R factors. Said otherwise, you can kind of, at least on some infinitesimal level, and I'm lying, but it doesn't matter, say that for almost every point, not only does it lie on the interior of a geodesic, but it kind of lies on the interior of 2 that cross in some perpendicular way, which means that almost every point splits 2 R factors. And you iterate this out to get 3, 4, 5, whatever. And the main theorem you get out of this is, so I'll state it with sort of its complete generality as it is now, is that if X is a limit space, then for almost every point, set a full measure inside X, the tangent cones at X are unique and isometric to RK. So almost every point looks infinitesimally like some Euclidean space. And in fact, you can push this and say it's actually rectifiable, which basically means these Euclidean spaces glue together like an almost manifold type of way. So this is really the starting point for a structure theory. To explain the references, so when Shiger and Kohling originally did this, I mean, this was their main application of this sort of almost version of the splitting theorem that's being done here. What they proved is that for almost every point there was some k for which the tangent cone was unique and isometric to RK. And they conjectured a constant dimension conjecture. So that is that this k didn't depend on the point. And that was proved about 4 years ago by me and Toby. Okay, so this is how you use rigidity theorems. And really, we're using an almost rigidity theorem here because we're really needing that to actually get all this to work machine-wise. But I should actually also point out that this proof of the splitting theorem has actually, at this point now, in just the last couple of years, been actually proved directly on the limit spaces without these almost versions. This was done by Gili in the context of these RCD spaces. I mean, these metric measure space notions of Ricci curvature. The moral of the proof is pretty much what we just went through, but the technical details are, substantially more difficult. There are a couple of original points in there.
So K is fixed here?
K is the same. That's right. That's the point. That K is the same as this for some K is this. K, you can say it, by the way, is less than or equal to n, the dimension of these guys. You can say that. So this thing has a dimension, is what that's being said. There's a dimension associated to the limit space. Okay. Now, it would be fantastic if I had sufficient time to actually explain the other rigidity theorem. I don't think I do, but we're going to do as much of it as we can in 4 minutes, and we're going to stop. So this will be a little lighthearted. So remember, what was the other sort of possible notion of rigidity we had here? In fact, this was already kind of brought up. Well, we have at every point a monotone quantity, right? So that is, we have this volume ratio, VR of x, which was just the volume of the ball of radius r around x over the volume of the ball of radius r in the corresponding hyperbolic space, if the lower bound is n minus 1. Maybe it's k. Doesn't matter. There is, by the way, and just so that I don't have to say technical things, in fact, that this is the nicer guy to work with in general. But if we're on a smooth space, which I want to be, then instead of lying to you, what I'm going to do is introduce one more monotone quantity, which is exactly the same. Instead of looking at the ball, you can look at the sphere of radius r and divide it by the corresponding volume of the sphere in your corresponding space form. It's really the same, but I'd have to say something technical about this one, which I don't want to do. So a very reasonable question here is, what happens if you have two radii for which this is the same? It's a monotone quantity, so what happens if at r equals 1 and r equals a half, what would happen if these ratios were actually equal? So this is a very hard thing to happen. But the basic theorem here, and my goal here had actually been to define for you carefully what a cone space is, but instead I'm just going to write it and describe for you what it is in pictures, because we have 2 minutes. So I'm going to assume non-negative Ricci, but that's not super necessary, actually, if you just change it. Take some space with non-negative Ricci. And let's look at x and m, such that for two radii, our monotone quantities doesn't change in between. Then, in fact, there exists a smooth manifold whose Ricci curvature is bigger than or equal to n minus 2. I'll explain where that number comes from. Such that if we look at the annulus around x, so here's our x, here's our r naught, here's our r1. So if we look at this annulus here, that's this region here. And the annulus between r naught and r1 of x is isometric to the annulus between r naught and r1 around y, where y is the cone tip of the cone point. of C of y. So what we're saying pictorially, what's a cone space? A cone space, right? Here's our manifold y, and we just sort of cone it out. And sorry, there's not enough time to give you a precise definition, but you can see it pictorially. And the point is that if we have two radii here where this monotone quantity doesn't change, say between here and here, then in fact you have to be exactly isometric to such a thing in between here. It's a very tough thing to do. Right? You have to be very rigid. This is sort of the basis for most of the structure theory for non-collapse spaces, but there's not time, so I'm done.